Swayam Prabha. Digital India. Educated India.
Hello and welcome to the module 7 lecture 8. What we have been doing so far is ordinary differential equations, the initial value problem. In the previous lecture we have considered some of the advanced techniques for solving the ordinary differential equations. Specifically we started off with the Runge-Kutta method, and in the previous lecture we talked about the Richardson's extrapolation and the adaptive step sizing techniques, and finally we discussed very briefly about what is known as stiff system of ODEs. Okay, so what we did in Richardson's extrapolation is starting with time ti, we used one iteration of Runge-Kutta method or any method for that matter of our choice, and from ti we go to ti plus 1. So within a single step, so we get yi plus 1 computed at computed using a single step method, that we will get it as equal to yi plus h times s of yi comma ti, okay, where this is going to be any method of our choice. So in the Runge-Kutta fourth order method we will have s as weighted sum of slopes computed at 4 different points, that means w1 k1 plus w2 k2 plus w3 k3 plus w4 k4, that is what we get for rk4 method. Okay, we repeat the exact same procedure again for a different step size for half the step size. So we will, when we do this for half the step size, we will get yi plus 1 h by 2 equal to yi plus h times s of yi comma ti, or I will write this as yi plus half h by 2 as yi plus h by 2 multiplied by s of yi comma ti, and yi plus 1 computed with slope h by 2 is going to be equal to yi plus half h by 2 plus h by 2 multiplied by s of yi plus half comma ti plus half. Okay, so this is using one step, this is using two steps. Okay, next we defined our delta as equal to yi plus 1 h by 2 minus yi plus 1 h. Okay, this is how we defined our delta. In Richardson's extrapolation what we do is that a higher order accurate solution okay, the higher order accurate solution can be obtained as yi plus 1 h by 2 plus delta, actually not delta by 15, the value of 15 was for RK4 method, 2 to the power m minus 1, where m is local truncation error minus 1. Okay, so for RK4 method the local truncation error is h to the power 5, so m becomes 5 minus 1, that is 4, so 2 to the power 4 minus 1. So for RK4 y nu is yi plus 1 h by 2 plus delta by 15, and the true value y bar is going to be equal to this guy plus the error, and this error is order of or the order of accuracy for this particular method is h to the power 6. Okay, so we have gone from h to the power 5 accurate method to an h to the power 6 accurate method by essentially by using a one step solution and then a two step solution, and then using the difference between these two solutions in order to compute a higher order accurate solution. So this is what we covered in the Richardson's extrapolation, and then we said that we can use this value of delta in order to get adaptive step sizing. Basically it will give you an idea of what the order of accuracy at that particular implementation is going to be. So in adaptive step sizing, what we said was h nu divided by h to the power 5 is going to be equal to epsilon tall divided by delta. Okay, and in order to choose our h, the desired h nu, we are going to use h nu is going to be equal to h multiplied by epsilon tall by delta to the power 1 by 5. Okay, so this is what we obtained when we wanted to use adaptive step sizing for the Runge-Kutta fourth order method. Okay, this is valid for RK4 method. For RK3 this is going to be 1 by 4, for RK2 it is going to be 1 by 3 and so on. Okay, this particular exponent basically depends on the order of accuracy of these methods. Okay, so this is essentially what we had covered in the previous lecture. What I am going to do now is talk about what is known as an embedded Runge-Kutta method, and this is one of the major accomplishments when it comes to the Runge-Kutta method is reduction. What embedded Runge-Kutta method allows us to do is it allows us to reduce the total amount of effort required in computing the adaptive step sizing through this particular technique. So I will show you what we mean by this. Okay, so what we are going to do is we will start with y1 and try to use method 1 to go to y I plus 1. Okay, and this particular method is would be of order h to the power m accurate. Okay, we will use another method, let us call this as method 2, to go again from yi to yi plus 1. We are going to use the same step size. So here what we have done is we went from yi to yi plus 1 using one step and yi to yi plus 1 using two steps. Here we are not going to do that. Here we are going to choose one RK method in order to go from yi to yi plus 1. We will choose another RK method again to go from yi to yi plus 1. The second RK method has to be more accurate than the first RK method of our choice. So this particular method, let us say the order of accuracy is h to the power m plus 1. Okay, now let us call the difference between yi plus 1 using method 1 and yi plus 1 using method 2 as delta. Okay, keep in mind that when we are going to do the step size adaptation, at that time we have the absolute values is what we are taking. So it really does not matter whether we take the difference m2 yi plus 1 using m2 minus yi plus 1 using m1 or the other way around. So as long as we know what this difference is going to be, we are going to be good. Okay, so now what happens is that when you take the difference between the two, now let us write down what the true value is going to be. The true value yi plus 1 bar is going to be equal to yi plus 1 m1 plus say C1 h to the power m, and yi plus 1, the true value over here is going to be yi plus 1 m2 plus some other constant C2 h to the power m plus 1. Okay. Now when we subtract these two equations, let us subtract the first equation from the second equation. When we subtract the first equation from the second equation, we will get 0 equal to yi plus 1 m2 minus yi plus 1 m1 okay, plus C2 h to the power m plus 1 minus C1 h to the power m. Okay. We rearrange this is nothing but negative delta, and so we can rearrange this and write 0 equal to minus delta plus C1 h to the power m plus 1 minus C2 h to the power m, or we take delta on to the other side and we will be able to write this equation as delta equal to C1 h to the power m plus 1 minus C2 h to the power m. Recall what we have been doing so far all the time. What we have been doing so far all the time is the term which has the least accuracy is the term that is going to govern how good or how bad our solution is going to be. H to the power m plus 1 term is more accurate than h to the power m term for very small values of h. As a result of this is the leading term that governs the accuracy. Okay. So this term okay. As a result, if we are going to have another delta nu equation of this form, delta nu is also going to be some constant C2 to multiplied by h to the power m accurate, as well as delta is going to be C2 or rather negative C2 h to the power m accurate. Okay. That is because most of the error comes in because of neglecting this term. The errors because of neglecting this term are typically going to be an order of magnitude lower than the errors come by neglecting this term. That is kind of the reasoning that we have been using for so long. Okay. And then when we take the ratio between the two and we use the same manipulations as we have done over here, what we are going to get is that the h nu that we have to choose is going to be equal to epsilon tolerance divided by delta, absolute value of that raised to the power of 1 by m. Okay. So this is the result for choosing the step size based on the accuracy of results. Okay. So this is the result we are going to use to choose the new step size based on what we estimate is the accuracy of the numerical method for solving the ODE equation. So for example, we could use RK4 method and an RK3 method. RK3 method is order h to the power 4 accurate, RK4 method is order of h to the power 5 accurate. So if delta we write this as yi plus 1 RK4 minus yi plus 1 RK3, then h nu is going to be equal to epsilon tall divided by delta, absolute value of that to the power 1 by 4. Why 1 by 4? The leading error term from this difference is the error term because of the less accurate method RK3 method. RK3 method has a local truncation error of h to the power 4, that means m over here is equal to 4. So the h nu is going to be equal to epsilon tolerance divided by delta. Okay. So this is one way of doing adaptive step sizing, the another way essentially of doing adaptive step sizing. Okay. This is not how the embedded RK work. How the embedded RK work is quite a bit differently. What we try to do is delta we will get as equal to yi plus 1 from an RK6 method minus yi plus 1 from an RK4 method. Remember why we are doing RK6 minus RK4 and not RK5 minus RK4 is for one very simple reason, because RK6 method is h to the power 6 accurate, whereas RK5 method has the same order of accuracy as the RK4 method. Okay. As a result, we are going to take RK6 minus RK4 as the difference delta. Okay. So now when we take this particular difference delta, we will have in this term 1 epsilon divided by delta to the power 1 by m, this m is going to be equal to 5, that is because the leading error is governed by the RK4 method. Okay. But the catch is this, RK3 and RK4 methods, the various slopes are actually evaluated at different points. The whole idea behind an embedded Runge-Kutta solver is essentially this, that RK6 method and RK4 method are going to share the data points at which various slope calculations are made. Okay. And one of the first embedded RK method was what was known as the RK Fielberg method, and after that nowadays in early 1990s I believe there was a new method introduced known as the Cash-Karp modification to the embedded RK method, and I will just go over to the slides and show you what we actually mean by the embedded RK methods. So these are the parameter values for the Cash-Karp method of embedded RK. Okay. As you can see, this is the typical structure that we usually have, where C's are the weights that we will use, A's over here essentially resemble the parameters P, and the B's over here resemble the parameters Q that we have been discussing so far for the Runge-Kutta methods. Okay. So what we see over here is that the first 4 points will actually be used by the 4th order RK method, whereas all the 6 points are essentially what will be used by the 6th order RK method. The accuracy of this method will be h to the power 6, with Ci star the accuracy of this method is going to be equal to h to the power 5. The difference between the two, that delta, is going to be governed by the leading error term in the two equations, and the leading error term is going to be h to the power 5. So what we do is essentially we calculate the slope at fi, calculate the slope at fi plus 1 by I plus 1 by 5, slope at I plus 3 by 10, I plus 3 by 5, I plus 1 and I plus 7 by 8, and based on these weights we are going to finally calculate what the slope is going to be. This particular slope is going to give us h to the power 5 accurate results, and the next slope is going to give us h to the power 6 accurate results, and the difference between the two is going to determine what our next step size is going to be. Okay. So this is essentially what I wanted to discuss about the adaptive step sizing, about improving the accuracy using the Richardson's extrapolation, and finally about stiff ODE solvers. What we will do next is we will take up one simple example and try to solve that the same example in fact that we have been talking about so far. We will take that particular example once again, we will try to solve these equations using the RK4 method, and then apply Richardson's extrapolation to RK4 method and see how the RK4 method results are actually improved by applying the Richardson's extrapolation. That is what we will do one. The second thing we will do is also then use the same results in order to get the adaptive step sizing and determine what the next step size is going to be. Okay. So let us now go to Microsoft Excel. what I will do over here, so this is the, I believe this is the sheet that we used in the previous lecture in order to compare the global and local truncation errors. So what we want to do over here, excuse me, so what we want to do over here is compute the concentration at volume V equal to 5, starting with the concentration C0 equal to 1.0. What we will do is we will take a step of H equal to 5 and then well, actually we can't take a step of H equal to 5, let us take H equal to 2.5 and then repeat this with a step of H equal to 1.25. Okay, I am doing this so that the difference between the two methods becomes very evident. Okay. Of course, this has not changed because we have included dollar signs over here. So, I will just drag this, and that is really the beauty of Microsoft Excel, is it is very easy in order if we have to really solve this particular relatively easier problems. Okay. And K1 is F computed at Ci, K2 requires H. So, I will just go over here and I will drag it down. Same thing we will do for K3, I will take this and drag it over here. Same I will do for K4, I will drag this over here. S is nothing but a weighted average of these, so it does not use H over here at all. Okay, and I will delete these values. Okay. Now, C I plus 1 is going to be equal to C I plus H times S. So, I will drag this to the new H value. Okay. So, now we are all set, all we need to do is really take this value and just drag it below. Okay. And then we take all these values and drag them, and this is going to be the error. Okay. So, now what we have done is we have computed V at 2.5 and V at 5 using steps of H equal to 2.5 and step of H equal to 1.25. Okay. So, if we were to look at the values over here itself, these are the two values that we are going to get. So, the delta is going to be the difference between the Ci computed from two step procedure and the Ci computed from the single step procedure. So, delta at location I is going to be equal to Ci using H2 minus Ci using H1. Sorry, H by 2 and Ci using H. So, that is going to be our delta, and Ci new is going to be equal to Ci using H by 2 plus delta divided by 15. Okay. And this is our this is the value that we are going to get. Error we have, as we have computed over here, the error is the absolute value of the difference between true and Ci divided by the true value over here. So, the error that we will compute is going to be equal to ABS of true minus the newly computed value divided by the true value. Okay. So, as you can see, what happened was our error was 2 into 10 to the power minus 2 when we used 1 into 10 yes, in fact it was 2 into 10 to the power minus 2 when we used h equal to 2.5. When we decrease the h from 2.5 to 1.25, the error decreased from 2e minus 2 to 2e minus 3, and when we took the difference between the two and we added that difference to the more accurate value over here, at that time the error then reduced further to 8 into 10 to the power minus 4. Okay. So, as you can see, this is the result that you get for I at volume V equal to 2.5 using the Richardson's extrapolation method. Okay. Next, what we do in order to continue this further is we do not use this particular CI, we are actually going to use the more accurate CI in its place in this, and then we are going to continue this further. As I said, as I had mentioned before, it is actually much more tedious to calculate this using Microsoft Excel, and that is the reason why we have not done it. Let us give it a shot, let us see whether we are able to do this calculation or not. I am deleting those values really because those values are not going to be needed. Now I am going to copy this and paste it below. Okay. And we are going to start with value of Vi, and again this is also not something we will need, so we will delete this again. Okay. And I will write the second iteration using Richardson's extrapolation. Okay. So, the first iteration we went from 0 to 2.5 using the two methods, one was a one step method and the other was a two step method. I will write those things down also. Single step of RK4 and two steps of RK4. Okay. So, V is going to be now equal to 2.5 and the new V is going to be 5, and likewise here the V is also going to be 2.5. Okay. What I will do next is copy this value of Ci new and then paste it over here, paste special and values. I do not want the formula to be pasted, I only want the value to be pasted, paste special and values. Okay. So, in the second iteration using the Richardson extrapolation, keep in mind what we are not doing over here, we are not running the two RK4 methods independent of each other. We run the two RK4 methods once, we get the solution of Ci, numerically computed Ci here and here, we use these two numerical solutions in order to get the new Ci. This new Ci is more accurate than any of these two Ci's. Okay. Now, this is the best estimate of Ci that we have at volume 2.5. This is the estimate of Ci that we are going to use again with the RK4 method using single step H and RK4, the same RK4 method using two steps H. So, we have copied this particular Ci over here as well as over here. Now, we run this again. Okay. So, we have run this from 2.5 to 5 and we have run from again from 2.5 to 5, first using one step, next using two step method. Now, what we will need is we will need the same to copy the same thing down over here and then edit the results. The delta is nothing but this minus this. Okay. So, delta is the difference between the concentration computed using the two step method minus the concentration computed using the one step method. Okay. Ci new is going to be the Ci computed using two step method plus delta divided by 15, okay, and the error is going to be the Ci new minus the true value, absolute value of that divided by the true value, okay, and that is going to be our error. As you can see, again the error for the Richardson's extrapolation method is 5 into 10 to the power minus 4, whereas the error using the two steps of RK2 RK4 method was 1 e minus 3, whereas using single step of RK4 method was 1 e minus 2, okay. So we have improved the accuracy from 10 to the power minus 3 to 10 to the power minus 4. What this allows us to do essentially is this: it allows us to take larger step sizes when we try to do these computations using the RK method, okay. So this is really what I had to discuss about the Richardson's extrapolation. Richardson's extrapolation first iteration. Okay, and this is the result, okay. So what we have seen now is you start off with two different ways of computing any particular ODE solution. One is has a higher accuracy than the other. You take the difference between the two. Now this difference between the two says something about the accuracy of the overall numerical technique. This particular estimate of accuracy can be used in two ways. One, it can be used to improve the accuracy of the method that we are trying to use, and that is using the Richardson's extrapolation. An alternative is to go to adaptive step sizing in order to improve the step size based on what we want or what we desire the accuracy of the overall solution technique to be, okay. So the first part where we use Richardson's extrapolation to get a more accurate result is what I have just covered. Now what I will do is, again we will go back to Excel and cover the adaptive step sizing part, okay. The good thing now is I do not have to do a whole lot. I have to I will just copy this. So copy this, create a copy, and this has now created a copy, and I will rename this as adaptive RK4, okay, and the previous copy I will rename this as RK4 with Richardson's. Okay, so now let us go to the adaptive step sizing. We do not need any of this. I will show you the adaptive step sizing for one iteration only. Okay, so now we have adaptive step sizing in RK4, and we have computed the RK4 solution using h equal to 2.5 and h equal to 1.25. Let us say that the desired accuracy is going to be equal to 10 to the power minus 5. I have chosen the desired accuracy of 10 to the power minus 5 just to demonstrate how this particular method is going to work. It is 2 orders of magnitude higher than the accuracy is 2 order of magnitude lower, sorry, than the accuracy that our method is giving. So desired, or rather epsilon tall, is going to be 1 e minus 5, okay. So that is the desired accuracy. I will just take this, pull this over here. We do not need the Ci new and error actually, okay. So our desired tolerance value is 10 to the power minus 5, whereas the delta that we are getting, the difference between the Ci and computed using h by 2, and the Ci computed using h is 5 into 10 to the power minus 3. Okay. So, h nu is what we will compute, and I will just increase the font size over here. Okay. Recall h new is nothing but h old multiplied by epsilon tall divided by delta raised to the power 0.2. Okay. So, that is what I am going to compute. Okay. So, h new is going to be equal to h old, which is 1.25 multiplied by ABS absolute value of epsilon tolerance divided by delta to the power 0.2. Okay. So, the h nu that we get is going to be 0.35. Okay. So, what this says is that in order to get the desired accuracy, we are using very large step sizes over here. We ought to be using much smaller step size than the step sizes that we have used. So, we need to decrease the step size to 0.35. Okay. So, what I will do over here is I will go back at this step and give h equal to 0.35067, and when I give that, I now get the accuracy that now I get is higher in fact than the accuracy that I have asked my particular method to give. Okay. So, with this particular h value now, so what we did is this, is we used initially the h value of 1.25 and h value of 2.5. What we then realized that the accuracy is not very good. Okay. The accuracy that this particular method provides is much less than what the accuracy that we have asked our method to give, and when we do that, what we actually get is that we get an error which is a fairly low value. Okay. So, this is how we are going to proceed with our numerical method. Okay. So, once we use this h equal to 0.35, okay, we go on to h I plus 1, we will use the h equal to 0.35 once again and h equal to 0.7 once again. So, from 0.35 volume we will go to volume of 0.35 to 0.7, and from 0.7 to 1.05. So, we are going from 0.35 to 1.05 in 2 steps, then we will go from 0.35 to 1.05 in a single step. Find the delta value by taking the difference between the concentration values that we obtained over here. Okay. And based on this delta value and based on this particular formula, we will compute the new h, and we will keep repeating this over and over again until we reach the volume v equal to 5. What I have shown you, hopefully that you have gathered with Richardson's extrapolation method, is that by using this method we can get a higher order accurate solution by using 2 low order accuracy solutions. That is what the aim of Richardson's extrapolation is, and I hope what I have conveyed to you using the adaptive step sizing example is that if we choose a step size too large, for example a step size of 1.25 for the plug flow reactor example is indeed too large under those conditions. If we use a very large step size, we can use this adaptive step size to reduce the next step size that we are going to use. Likewise, if we were to use a very small step size, let us say we were to use a step size of 0.1, we would have been able to increase that step size from 0.1 to a higher value in the next step. In fact, we can actually quite easily perhaps demonstrate that if we start with an h of 0.1 and an h of 0.05. Okay, then the delta accuracy that we are going to get, or sorry, from h of 0, let's try 0.2 and then we will try h of 0.1. Okay. So the delta accuracy that we are getting is 10 to the power minus 7, and the tolerance that we have asked is 10 to the power minus 5. Okay. And the h that we are going to get is going to be equal to 0.1 multiplied by this particular value, and the steps, the result that we will get over here is going to be 0.24. Okay. So as you see, instead of choosing a step size of 0.1, our adaptive step sizing technique has said that it would have been okay if we had chosen the step size of 0.24 as well. Okay. So that is essentially how the adaptive step sizing actually works. If we look at some of the more theoretical results from the numerical recipes textbook, they will recommend that when you are increasing the step size, we increase it in a more conservative way. So for increasing the step size, we are going to have this to the power 0.25, and when we are decreasing the step size, sorry, when we are increasing the step size, we can it is going to be h to the power 1 by 4, and when we are decreasing the step size, it is going to be h to the power 1 by 5. There are theoretical reasons as well as practical reasons why these recommendations are given. I won't, of course I won't go into details, because already adaptive step sizing is indeed a fairly advanced topic for a typical undergraduate course. Okay. So that is what I had to cover on adaptive step sizing. Now we will go on to a new set of techniques. As I had said before, we will let's recapping what we had. So what we have covered is, in the previous lecture, are these methods. In today's lecture, we have talked about Richardson's extrapolation, adaptive step sizing, and taken up examples. Okay. Now what is left in this particular module is talk about the Adam-Moulton's family of methods, and that is what I am going to do in the rest of today's lecture and in the next lecture. So the methods that we have considered so far come under the umbrella of the Runge-Kutta family of methods, as well as after that we covered the predictor corrector methods. The third class of methods is essentially what is known as multi-step methods. So the multi-step methods, there are two types. One would be the Adams family of methods, and the other one is backward difference formula. Okay. A general way of writing the multi-step method is as follows. I will first talk about a little bit about the geometric interpretation of this, and then we will talk about how exactly we are going to get. Let us say we are currently at location I, the next one is location I plus 1, likewise the previous locations are I minus 1, I minus 2, so on and so forth. So I minus 1, I minus 2, I minus 3, blah blah blah. Okay. So let us say we are going to plot y versus t. Okay. So y versus t that we will get, let us say we have reached y versus t. In this we actually won't reach it like this. Okay. So what we have is I minus 1, I minus 2 and I minus 3, and let us say we have the yi computed at I minus 3, I minus 2, I minus 1 and I. Okay. Now what we can do is we can use this information. So what information is available to us now is y0, y1, so on up to yi minus 1 and y I minus yi. Okay. So this is one set of information available to us. We also know T0, T1, T2 up to Ti. This using this information, what is also available to us is F0, F1, Fi minus 1 and Fi. Okay, both this information are informations are available to us. Recall that the equation that we are trying to solve is dy by dt is equal to f of y comma t given y at t0 equal to y0. Okay, so this is the equation that we are trying to solve. Now given y0, we can compute all these values y1, y2, y3 up to yi, and having these values known to us, we can get f0, f1, f2 and so on up to fi. Okay. The multi-step methods, what we try to do is this: yi plus 1, we will write this as some kind of a weighted sum of the past y's as well as the past f. Okay. So we will write this as a0 f I plus 1 plus a1 fi plus a2 f I minus 1 plus so on up to an f I minus n plus 1. Okay, sorry, I minus n minus 1, no, okay, I minus n plus 1. Okay, so this is what we will get over here. That is the weighted average of the past function values plus b0 yi, or sorry, we will write this as plus b1 yi plus b2 yi minus 1 plus so on up to bn y I minus n plus 1. Okay. So we will write y as sum of the past function values and the sum of the past y values. Okay. And this is the overall general equation for any multi-step method. Okay. So this particular expression that we had written over here, I am writing it using the summation symbols at this, like this. Okay. I have written down this particular equation over here. Now I will just go on and explain how this Adams family of methods and the backward difference formula methods are going to differ from each other, and what that means really. So first we will talk about Adam-Bashforth method. Okay. In Adam-Bashforth method, what we do is we say that the a0s are a0 is 0 and all bj's are 0. Okay. So yi plus 1 is going to be computed based on the past f values or past slopes at the points that we have already computed. Okay. So this term disappears in an Adam-Bashforth method, this term also disappears in the Adam-Bashforth method, and we will get yi plus 1 equal to equal to a1 a1 fi plus a2 fi minus 1 plus so on up to an fi minus n plus 1. Okay. and this is going to be an nth order Adam-Bashford method. Okay. Now this method is an explicit method because yi plus 1 depends only on the past points, and we are assuming over here that the past points are known to us. Okay. So this is going to be an explicit method. If a0 is not equal to 0, what we get are implicit methods, and that is the next family of methods known as Adam-Moulton's methods. Okay. And the nth order Adam-Moulton's method is going to be yi plus 1 equal to a0 fi plus 1 plus a1 fi plus a2 fi minus 1 and so on up to an fi minus n plus 1. Okay. So these two are the Adams family of methods, and finally we have the backward difference formula, and the idea behind the backward difference formula is we do not worry about the function values in the past, we only worry about the yi's in the past. So the backward difference formula is going to be yi plus 1 is going to be a0 fi plus 1 plus b1 yi plus b2 yi minus 1 and so on up to bn yi minus n plus 1. Okay. And so we will have an nth order backward difference formula. The way of computing the backward difference formula is fairly straightforward. What we do is we describe df by dt equal to nothing but dy by dt as nothing but the numerical difference between the past points, and we will use this in order to derive the backward difference formula. Adam-Bashford method and Adam-Moulton's method will be using the Newton's backward difference interpolating polynomials. We will fit them to the past function values fi minus 1 up to fi minus n plus 1, and we will use those results and integrate them in order to get yi plus 1 using the Adam-Bashford or using the Adam-Moulton's method. The derivation of these methods is something that I will cover in the next lecture. Thank you.